Yes, sir.
Screen is visible.
Yes, sir.
Okay. Also, system uses certain codes. One is vector code, another one is non-vector code. Under vector code, we have a code called BCD. Under non-vector code, we have a code called gray. BCD stands for, also another code is there, under non-vector code, which we call this as XS3 code. Mostly vector code, BCD, binary coded decimal. And under non-vector code, we are using a code called gray code. Let us see, this BCD code is a 4-bit number. We are writing 1, 2, 4, 8. The name of this code is 8421 code. Suppose I want to find the value of 3. How I will get 3? Now if I will add 2 plus 1, it will give 3. So the number which will be used, that will put it as 1. Number which is not used, that will put it as 0. Suppose 9. 8 plus 1, 9. So 1, 1. Rest will be 0. Suppose I want to find the value of 7. 4 plus 2 plus 1 is 1, 1, 1 is 0. Means that in this code, we are adding the digits to find a specific value. BCD, binary coded decimal. And you know that in case of your decimal number, we have the values from 0 to 9. But the value of 0, this will be no digit will be added, so this is 0. Suppose 5. 4 plus 1, 5. This will be 0, 1, 0, 1. 4 and 1 are used. So if you see this specific, this is 4, 2 to the 3, this is 8. So this BCD code, 8421 code, it is of 4-bit. Suppose you are using a number like 37. And this particular BCD code we are using in our calculator. You know that calculator is also an electronic device. So in calculator, there is no key like 37. First of all, we have to press 3. So whenever we press 3, the value will come up as 0011. When 7, we have the value as 0111. So this is in decimal, and accordingly, this value is in BCD. Are you getting my point? 37 in decimal, if you convert this number to its corresponding BCD, this will be coming up as 0011 0111. Right?
Yes, sir.
Okay. Someone has some. Someone wants to join, but let me join through mobile. Okay. Astos, you have joined in 2 devices,
No, sir. One device.
but it shows 2.
Sir, I got logged out. Then I have rejoined. That's why it's showing.
No, it's okay. Okay, BCD arithmetic what happens? Suppose you want to add a number like, let's say 37 plus 44. What is the value? 7 plus 4, 11. We're cracking one carry. Then 4 plus 3, 7 plus 1, 81. But whenever you add in calculator, 37, this will be converted to its value like 0011. 7 is 0111. This is in BCD. Similarly, 44, 4, 0100, again 4, 0100. This is in BCD. So when addition takes place, we'll have 0011, 0111 plus 0100. Someone might want to join. Now someone left. Zero one double zero plus zero, sorry, plus 0100. One, one, 1 plus 1, 0 with carry 1, 1, 1, 1, 0. So you know that in case of hexadecimal number system, also each digit will be represented in 4-bit form. So what is the value we'll getting? We'll get this is 7, 1011. This will be B. So result will be coming up as 7B. But in normal decimal number system, we have the values. What is the normal values? We have the number from 0 to 9. So whenever this type of number will come, automatically 6 will be added. 0, 1, 1, 0. 0, 1, 1 plus 1, 0 with carry 1, 0 with carry 1, 0 with carry 1, again 1 plus 1, 0 with carry 1, 0 with carry 1, 0 with carry 1, 1. So what is the value? This is 8, this is 1. It means that you have the number from 0 to 9 in decimal number system. But in hexadecimal number system, we have the values from 0 to 15. So if your number is greater than 9, then we will add 6. Why 6? Because if you count 10, 11, 12, 13, 14, 15, total it is 6. You understand? As it is 6, so automatically 6 will be added to give you the number in the form of decimal. Understand all of you? Hello?
Yes, sir. Yes.
Again, someone?
Sir, we are here.
Oh, you are here. Once actually I present the screen, I could not see any other of you. And I'm not using two devices. That's the problem. Okay. Let me do one thing. I want to join. Okay, shall we continue?
Yes, sir. Sir, you can continue.
Thing is that everybody join late, so each time I have to allow them. That's the problem.
Okay.
So have you understood how you'll get 81? In BCD arithmetic, in decimal number system, we have the values from 0 to 9. But while we are, as it is 4-bit representation, you might get this type of value like 1011 B. But the normal set, nobody understands what is B. For that reason, 6 will be added. Why 6 will be added? In decimal number system, we have the values from 0 to 9. In hexadecimal number system, as it is also 4-bit representation, we have the values from 0 to 15. So after 9 up to 15, we have the values like A, B, C, D, E, F. Right? To get the complete decimal value, 6 will be added if the value will be coming up as A, B, C, D, E, F. Clear? That's why we are adding this value. Clear, all of you? Hello?
Yes, sir.
Yes, sir.
Next, we'll be discussing about one important thing, that is floating point arithmetic. Sorry, we have gray code, na? Gray code is mostly used whenever we are transmitting data from computer to printer. When we are transmitting data from computer to printer, it will go and it will be converted to its corresponding gray code, and again there it will be reconverted to binary. As you know that your computer is an electronic device, it will accept only the values like 0, 1 or 1, 0. Let us take an example. Suppose we have a value like 1, 0, 0, 1, 1, 0, 0, 0, 1. Suppose this is in binary. I am giving you how you will convert the number from binary to gray. In case of binary to gray, this is your MSB. So MSB is constant, right? Then the subsequent bit will be added and the result will be stored. 1 plus 0, 1. 0 plus 0 is 0. 0 plus 1, 1. 1 plus 1, 0 with carry 1, omit the carry. So there are 3 points you have to remember whenever you are converting from binary to gray. First point, MSB is constant. Number 2 is the subsequent bits will be added and the result will be stored. And point number 3, in addition, if any carry term will come, then it should be omitted. 1 plus 1, 0 is carry 1, we are omitting the carry. Then 1 plus 0, this is 1. 0 plus 0, 0. 0 plus 1, this is 1. This is in gray. If you count the number of bits in binary, we will have 1, 2, 3, 4, 5, 6, 7, 8. You will get the same number of bits. 1, 2, 3, 4, 5, 6, 7, 8. If there are n number of bits in binary, then if you convert to its corresponding gray, you will get the same n number of bits. Understand? I'm repeating once again, to convert from binary to gray, we adopt a principle. Point number 1, MSB. This is your MSB. MSB, yesterday I had told, this is your MSB. This is your LSB. MSB stands for most significant bit. So MSB is constant. And point number 2, the subsequent bits will be added. So 1 plus 0, 1. MSB constant. Then 1 plus 0, this is 1. 0 plus 0, this is 0. Come on, my friend. MSB is constant. Then the subsequent bits will be added. 1 plus 0, 1. 0 plus 0, 0. 0 plus 1, 1. 1 plus 1, 0 with carry 1. We are keeping 0, omit the carry. Then 1 plus 0, 1. 0 plus 0, 0. 0 plus 1, 1. Right? The number of bits in binary will get the same number of bits in gray. Understand? Hello?
Yes, sir.
Now, if you convert gray to binary, same principle that MSB is constant. MSB is constant. Then the result will be added with the subsequent bit. This is your result bit. So 1 plus 1, 0 with carry 1, omit the carry. It means first MSB constant, binary to gray, MSB constant, gray to binary, same MSB constant. Point number 2, binary to gray, subsequent bits will be added and the result will be stored. Whereas in case of gray to binary, the result will be added with the subsequent bit and stored. Third part remains same. In addition, if any carry term will come, then it should be omitted. Right? Then 0 plus 0, 0. 0 plus 1, it is 1. 1 plus 0, 1. 1 plus 1, 0 with carry 1, omit the carry. 0 plus 0, 0. 0 plus 1, it is 1. This is in binary. If you see the number of bits in gray, you'll get the same number of bits in binary. What was the previous value? 100, 1100, 1. 100, 1100, 1. Have you understand? In gray to binary, MSB is constant, then the result will be added with the subsequent bit and stored. In addition, if any carry will come, then it should be omitted. Clear? Only for your understanding purpose, I am putting this arrow mark. So that in future, if you refer, you know what was done. Future, when you see, you can remember what has been done. Okay? Hello? Have you understand?
Yes, sir. Yes, sir.
Okay. This is the principle of binary to gray and gray to binary. Then now we'll be discussing one important thing, that is floating point arithmetic. Floating point arithmetic. For the timing, you just remember that registers are mostly used for storing. That means registers used for storing. Whatever things you have stored, that should be used in the computer for storing. Suppose, let me finish with the decimal number system, then we'll go for the binary. Am I right? Because you are all familiar with decimal number system. For that reason, let me start with decimal number system. Okay? Or directly I'll tell about binary. Hello? Am I audible?
Yes, sir.
So I am asking whether I'll go for decimal, directly binary. It will teach you decimal because all of you are familiar with decimal number system. For that reason, I'm asking you. If I'll go for decimal number system, it will be easier for you to understand. Shall I go for decimal or directly for?
Sir, decimal.
Yeah, you can decimal, sir. Please go for.
Okay, in decimal number system, you see, suppose I will take a register of like this. I'm putting one decimal point here. This is your assumed decimal point. And let this be the sign. Let's say this is plus, because your number is either positive or negative, right? Suppose I'll write 1, 2, 3, 4, 5, 6. So if you write this, it should be treated as plus 123.456. Am I right? Because my assumed decimal point is here. Understand? So the value is plus
Yes, sir.
123.456. So if I store with this particular register, then my maximum and minimum is 999.999. The maximum value is 999.999 plus, and the minimum value is minus 999.999, right? So if I want to store
Yes, sir.
more value, then what I have to do? I have to increase this size. If I want to store more value, then I have to increase this size. Again, if I want to store less value, which is less than minus 999.999, same thing, I have to increase the size. Okay. So who is the father of your computer? Who is the father of computer?
Charles Babbage.
Charles Babbage is the father of computer. So when he developed the system, it is just like a size is very big, just like a room. But nowadays we are using laptop, palm top, very small devices. How it has been done? It has been done by using some modification in that particular machine. So the thought of, and they try to find by putting these numbers in the form of matrica and exponent. Matrica and exponent. Here, this is the base of 10, this is the exponent. So this 123.456 can be written as 0.123456 into 10 to the power how much? 123.456. I can replace this by writing in the form of matrix and exponent. As this is a decimal number system, so it is the base is 10. So this will be 0.123456 into 10 to the power 10 to the power
3.
10 to the power 3 plus 3. Okay. So your matrica, for matrica I am writing M. Matrica is 0.123456 and exponent is 0, 3. So I am keeping 2 digits for exponent. Now what happens? This 6 digit, I am defining this. I am keeping this to this place for the exponent. Exponent of whom? Of the number, and this portion I am keeping as the matrica, and this is your sign bit. So this will be 1, 2, 3, 4. There is no space, and exponent is 0, 3. Understand? But
Yes, sir.
another problem arises. Suppose a number is 0.00012345. This can be written as 0.12345 into 10 to the power
minus 3.
10 to the power minus 3. But there is no space for storing this minus or negative number. That means in this case, this is called normalized floating point. Normalized floating point. Normalized floating point method, there should not be any zero just after the decimal point. That means we cannot put any zero after the decimal point. That is known as your normalized floating point representation. And always your number should be represented in normalized manner. Understand?
Yes, sir.
Here we have the plus. This plus. This is the sign of the number. Plus. If it is minus, it should be minus. Understand? But there is no space for the exponent. So how the negative number will be stored? For that reason, they thought of and find and how it has been possible, they will take a scale. So in exponent, we are taking only 2 digit. So minimum is how much? 0, 0. If I put here, minimum is 0, 0 and maximum is 99. Am I right?
Yes. Yes, sir.
0, 0 is the minimum and maximum is 99. With this 2-digit number, right? Then find out the mid value. What is the mid value? What will be its mid value?
50.
Hello?
50.
How it is 50?
It's counted from 0, 0.
Counted from 0, 0. So mid value is 50. So this, they thought, take this 50 as the base value. 50 is the base value, which is correspond to 10 to the power 0. Then this is called the floating point exponent. What is the floating point exponent? The actual exponent will be added with 50. So 50 plus 3, because previous case is 3, your answer will be coming up as 50. If it is minus 3, the 50 plus minus 3 is equal to 47. That means 50 correspond to 10 to the power 0. Any value or any positive exponent which is greater than 50 is the positive exponent. Less than 50 is the negative exponent. Understand? So what value will be stored here? This will be 53, which we call this as floating point exponent. Understand?
Yes, sir.
So if we'll store within this value, what is the range now? Range is minimum is 0.1, because in the Mantis part, there should not be 0 after the decimal point. So what should be the minimum? The minimum should be 0.1
Yes, sir.
into 10 to the power minus 50. Because 50 minus 50 will be 0. This is the minimum value. Do you understand? And maximum 0.1 into 10 to the power 99 minus 50. So it should be 49. This is your maximum value. Are you getting? Have you
Yes, sir.
understand? The minimum
Yes.
value is 0.1 into 10 to the power. That means previously your range was plus minus 999.999 with this 6-digit format. Now, with this 6-digit format using floating point arithmetic, we will get this 0.1 into 10 to the minus 50 is the minimum value, and maximum is 0.1 into 10 to the power 49. So this 0.1 into 10 to the 49, which is a very bigger value than plus 999.999. So if you suppress this one, this will be coming up as 10 to the power 48. Am I right? If you suppress this 0.1, this will be coming up as 10 to the 48. If you suppress this 0.1, we'll get 10 to the power minus 51. But in case of floating point arithmetic, we cannot suppress because it should be always represented in the form of multi-cell exponent. Understand? So your minimum, if someone asks you what is the range now, the range is 0.1 into 10 to the minus 50 to 0.1 10 to the power plus 49. But before it was minus 999.999 to plus 999.999. So if you compare this value, it is quite greater and quite less value in comparison to the previous one. Am I right?
Yes, sir.
So with this format, if you want to store more number or if you want to store less number, then only we have to increase the size of the register. Otherwise, with this register, we can have this much of values. Understand?
Yes, sir.
Now write down one question. Represent 53 53.625 to the base 10. Represent 53.625 to the base 10 in binary floating point representation. In binary floating point representation in a 16-bit register. In a 16-bit register in which 9 bits for mantissa, 6 bits for exponent, and 1 sign bit. 9 bit for mantissa, 6 bit for exponent, and 1 sign bit. Total number of bits is 16. Right? So how we will solve this one? First of all, we'll make this to its corresponding binary number. So what is its corresponding binary equivalent? 53.625 to the base 10. If we convert to binary, what will be its binary equivalent? Can anyone tell? What is the value? 1, 1, or 40, 1, 1, 0, 1, 0, 1.101 in binary. All of you agree? 53.625 to the base 10. If you convert this to binary, this will be coming up as 110.101 in binary. Have you understand? Hello?
Yes, sir. Yes, sir.
You know how
Yes,
to
sir.
convert, na?
Yes,
Okay.
sir.
This will be represented in the form of multi-channel exponent. So 0.110, 101, 101 into 0.110, 101, 101 into how much? Huh? Because in the floating point exponent, you have to represent each number in the form of multi-channel exponent, na? So 1.110, 101, 101 into, let us speak. Huh? Any one of you tell?
10 to the power 6.
10 to the power 6.
6.
But thing is that we are using binary number system. Okay. So as you are using binary number system, there is no base like 10. Base is 2. So 2 to the power 6. Understand why it is not 10?
Sir, binary.
As it's a binary number system, so instead of 10, it should be 2. So what is your mantissa? Mantissa is 0.110, 101, 101. What is your exponent? 6, which is equal to 110. What is floating point exponent? Which is most important? You see, make the scale. Minimum is 6 number of 0. Maximum is 6 number of 1. What is the mid value? Just in the previous example, we are having 0, 0, 99. All of you told mid value is 50. So here, what is the mid value? Can anyone answer? What is the mid value? No? Don't know? Hello? Am I audible?
5554.
Oh, it's wrong. I am talking about binary number system. In binary system, where you will get 5? It should be 1, 5 number of 0. Are you getting my point? Because we are solving all this in the form of binary. In binary, it should be 6 number of 1. In decimal, it should be 6 number of 9. So if you convert this is 0. If you convert this will be coming up as 63. So 0 to 63, total 64 divided by 2, 32 is the mid value. If you convert this 32 into binary, it will be coming up as 1, 5 number of 0. Remember, if this type of, here I am taking the example of 6 bit. If 8 bit will come, 8 number of 0, 8 number of 1. Bit value will be coming up as 1, 7 number of zeros. If you do not understand, then you can take or convert this to corresponding decimal and divide it, because very small value that you can know. Clear? So the mid value 1, 5 number of 0 will be added with 1, 1, 0, which will give you 1, 0, 0, 1, 1, 0. This is the floating point exponent. Understand all of you? All of you understand?
Yes, sir.
Hello?
Yes, sir.
Okay. Now you will represent this in a 16-bit format. One, two, three, four, five, 6. This is your floating point exponent. This is your mantisha, and this is your sign bit. That means always MSB is your sign bit. Sign bit 0 or positive, 1 or negative. It's a positive number, so 0. What is your mantisha? 1, 1, 0, 1, 0, 1. 1, 1, 0, 1, 0, 1, 1, 0, 1. And what is your exponent? 1, 0, 0, 1, 1, 0. This is the representation. Clear, all of you?
Yes, sir.
Hello? All of you clear?
Yes, sir.
Yes, sir.
Okay. Next we have the error detection and correction. Error detection and correction. Remember, for this error detection and correction, we must familiar. I'm just giving one example. There is a match was held at Melbourne City, Melbourne, between India and Australia, and we are watching that match here in our home. Am I right? How it is possible? This is possible due to communication. How it has been done? Some cameras are there in the field. They are capturing the things, what is going on there. Then they are sending through satellite, and in your home, your satellite receives, and accordingly, you will get that. So, in the form of electronics, those who have studied physics, they must know the uh, Photograph which is captured, it has created a signal that is called modulating signal. And how this modulating signal goes, it will mix up with a signal that is known as your carrier signal. About all these signals you will be studying in your computer network. Then create a signal that is known as your modulated signal. This modulated signal flows, and your antenna receives this modulated signal and it throws the carrier signal. What remains? The modulating signal. That means the thing which was there in the ground, you are watching in your TV. Right? For this carrier signal, we use a word which is known as your parity. What do you mean by parity? Parity means counting the number of words in a particular word. In a particular word, how many number of ones are there? That is the parity. For example, my word length is 4. So 1 0 1 1 0 triple 1 1 0 0 1 0 0 1 1 1 1 1 triple 0 1 0 1 0 1. Right? So what is the parity here? 3. Well, count. My word length is 4 bit. There's a number of 1. This is 3. This is 2. This is 2. Here it is 4. Here it is 1. Here it is 2. Are you getting my point? What is parity?
Yes, sir.
Parity means counting the number of ones in a particular word. So in my word, I'm taking the word length of 4 bit. So total number of one available in this word. Here the number is 3. Here 3. Here 2. Understand all of you? Again,
Yes, sir.
it has been divided into two parts. One is even parity, one is odd parity. Even if even number of 1, odd if odd number of 1. This is odd parity, even parity, even parity, even parity, odd parity, even parity. If even number of 1 is available, then we call this even parity. And if odd number of 1 is available, then we call this odd parity. Right?
Yes, sir.
Now, if you see our positions like this 1, 2, 3, 4, 5, 6, 7, 8, and continue. Remember, parity always takes the position 2 to the power n. Parity always takes the position 2 to the power n, where n is any positive integer starting from 0 to n. Parity always takes the position 2 to the power n, where n is any positive integer starting from 0 to n. So 2 to the power 0, 1, this is parity position. 2 to the power 1, 2, parity position. 2 to the power 2, 4, parity position. 2 to the power 3, 8, parity position. Then 2 to the power 4, 16, parity position. Understand? But the rest positions which we left, that is known as your data position. D3, D5, D6, D7, D9, likewise. So only to distinguish between parity and data, I am using the symbol P and D. But in your syllabus, you are initially will send 4 bit of data. So while you are sending 4 bit of data, so this portion is not required. D7, D6, D5, D3, 4 bit of data, automatically 3 parity bit will be added, which forms a 7-bit pattern. This 7-bit pattern is known as your Hamming code. This 7-bit pattern is known as your Hamming code. Why Hamming code? Because it was developed by the scientist Hamming, and according to him, it is known as your Hamming code. Right? Let us start with construction of Hamming code. D7, D5, D6, D5, D4, D3, D2, P1. Suppose I want to send a data bit of 1011. So construct the Hamming code with the data bit 1011. That 1011 is your modulating signal. So the modulated signal will be attached. What will the modulated? That is P1, P2, P4. This is your carrier signal. So to know the position of P1, P2, P4, there is a formula. That is P1 is equal to, we'll check the position 1, 3, 5, 7, P2, 2, 3, 6, 7, and P4, 4, 5, 6, 7. And always we'll check for the even parity. Understand? So how we get the position? Let us see. We have the values like P4, P2, P1. I am writing in this way. P4, P2, P1. So as there are three variable, number of possible cases is 8, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. We will convert this. This is 0 into decimal. 1, 2, 3, 4, 5, 6, and 7. Right? You know that one thing, that 0 means false, 1 means true. Agree, all of you? All of you agree? 0 false, 1 is true.
Yes, sir.
Hello? A function is
Yes,
said to be true if its value is 1, and a function is said to be false if its value is 0. Right?
yes, sir.
So when P1 is true, this position, this position, this position, this position. This is 1, 3, 5, and 7. I've written here 1, 3, 5, 7. Similarly, P2, 2, 3, 6, 7, 2, 3, 6, 7, and P4, 4, 5, 6, 7, 4, 5, 6, 7. Are you getting where I got this value?
Yes, sir.
Yes.
Where I got this value, all of you understand?
Yes.
Yes, sir.
Okay. Now you see, in each case, the first position value we do not know. And we have to find out the value of P1, P2, and P4. P1, I do not know. 3, there is a 1. 5, another 1. 7, another 1. So total number of 1 is 3. Am I right? Total number of 1 is 3. It is even or
Yes, sir.
odd? It is even or odd?
Even.
3 number of 1, it is even.
Odd.
Huh? Either even or odd, that I know. There are 3 number of 1, it is odd. So to make it even, I require another 1. It means that whenever you count, if you found the number is odd, then the value of this is 1. And if it is even, value is 0. Why? Because if you put another 1 in the odd value, it will be going up, or it will give you even. In case of even number, if you put another 1, it will give you odd, and always will check for the even parity. Have you understand?
Yes, sir.
Then what is P2? 2, 3, 6, 7, 2, we do not know. 3, there is a 1. 3, there is 0. Sorry, 3. Then 6, 0, 7. So we'll have 2 number of 1. It is even. So as it is even, value is 0. Then P4, 4, 5, 6, 7. 4, we do not know. 5, there is a 1. 6 is 0. 7 is another 1. So total 2 number of 1. As it is even, value is 0. So what is the value? P4 is 0. P2 is 0. P1 is 1. This is the Hamming code 1011. When you are sending the data bit 1011, automatically this 3 bit will be attached and form a 7-bit code, that is 10101001. This is the construction of Hamming code. Understand?
Yes, sir.
Now write down one question. In a transmission, the receiver got a pattern. 111010101. In a transmission, the receiver got a pattern 1110101. Is there any error? If yes, then in which data bit? If yes, then in which data bit? And what is the correct data? What is the correct data? Let us see. D7, D6, D5, D4, D3, D2, D1. Here you will find all 7 bits are given 1, 1, 1, 0, 1, 0, 1. So what happened? Already you know the value of P1, P2 and P4. So for correction purpose what happened? This P1 now it will be replaced with the variable X at same position 1, 3, 5, 7. P2 will be 2, 3, 6, 7 and P4 will be, sorry, P2 will be Y and P4 will be Z. This will be 4, 5, 6, 7. As you know the positional value of P1, P2, P4, I will take another variable like X, Y, Z. Again, we check for the even parity. So P4 will be replaced with Z. So same formula, this will be Z, this will be Y, this will be X. So you'll get the same value 1, 3, 5, 7, 2, 3, 6, 7, 4, 5, 6, 7. Okay. Now you find out the value of X. 1, 3, 5, 7. 4 number of 1. So what is the value? As it is even, value is 0. Understand? If it is even, value is 0. If it is odd, value is 1. Understand?
Yes, sir.
Then what is Y? Now 2, 9, 3, there is a 1, 6 another 1, 7 another 1. So 1, 2, 3. 3 number of 1. So it is odd. To make it even, I require 1.
1.
Then Z, 4, 5, 6, 7. 4 position 0, 5, 6, 7, 5, 6, 7, 3 number of 1. The value of Z is equal to 1. Understand? Now question is there any error? Yes, there is error. If X is equal to 0, Y is equal to 0, Z is equal to 0, then there is no error. That part I will be coming just after explaining this one. Is there any error? No, yes. Why? Now X is 0, but Y and Z are not 0. For that reason, there is error. Which data bit? The formula is ZYX because we are writing P4, P2, P1. It will replace with ZYX. What is Z? Z is 1. We are getting Y is equal to 1. X is equal to 0. So if we convert to decimal, this will be coming up as 6110. If we convert to decimal, this will coming up as 6. It means error lies at 6th position. Where the error lies? Error lies at 6th position. So this position you are getting the error. So what is the correct data? You just change this to 0. If it is 0, it should be changed it to 1. If it is 1, change it to 0. Remember, through this method, we can correct only one bit of data. If there will be error in single bit, then it should be corrected. Otherwise, sometimes while watching your TV, you will find some HE figure comes, and sometimes it will write that no signal. No signal means there is HE means there is some error. It tries to rectify, but if more than one bit error, it cannot rectify. Just throws, and you will get no signal on your TV. Understand?
Yes, sir.
Now, if the question will come like this 1 0 1 0 1 0 1, here if you check, you will find X is equal to how much? Now 1 3 5 7 0. What is Y? 2 3 6 0 7. Y is 0. What is Z? Z is equal to 4, 5, there is 1, 6 is 0, 7, another one, 2 number of 1, Z is equal to 0. So when X is equal to 0, Y is equal to 0, Z is equal to 0, there is no error. Because if you find the position, you will find the position this will giving you Z, Y, X will be 0, 0, 0. But in our discussion, there is no 0 position. We are starting with the position number 1, 2, 3. Understand? So if X is equal to 0, Y is equal to 0, and Z is equal to 0, then there is no error. And all these things was developed by the scientist Hamming, and according to him, it is known as your Hamming code. Clear?
Yes, sir.
Okay. Stop it here because you may have another class at 8. No class.
No, sir, we don't have any classes.
Okay, but if they have provided me any other class, then only I will take. Otherwise, I've just completed this arithmetic part. Then the most important logical part will start. Let us see if they will provide some more class. Then I will continue. Have you understand till date what I have discussed? All of you understand?
Yes, sir, understood.
Remember, this paper is very easy to understand, like organic chemistry. It is very easy to understand in the class, but while you will solve, it may create problem. So whatever things we have discussed, try to solve some more problems so that it will be easier for you. Or else if you want to any clarification from me, then you can just note down my number. I'm writing here 8895019850. You can ping me through this number
8895
8895019850. It's my calling number. So before, if you want to face any problem here in this part, you can directly ask me. Okay?
Yes, sir. Thank you, sir.
Okay. Let us stop here.
Yes, sir.
Okay. Most of you have not written your name with roll number. Up to Asutosh Das, it is okay. I got the roll number. I can get the name from the list. Roll number 1, roll numbers, 701, 785, Lakshmikanta Bira. Roll number is, just write it down, 200316189. George Lima, you have written once, na?
Already have written.
Oh, you have written initially.
It is not visible in my, so I couldn't. I thought I will be writing it again.
Okay. Monica Das. 200470688. Okay, let us stop here. If they will provide more class, then we will take. Otherwise, you can contact me over phone. Chalo, bye.
Thank you very much, sir.
Thank you, sir.
Thank you, sir.